Okay, so hi again. So let's learn how we can use the second derivative to find out if a function is convex or concave over an interval or has an inflection point. So we're going to begin by looking at whether the function is convex or concave. Okay, so here we have the key information from your books. Okay, and that is that if the second derivative, if the value of the second derivative is positive at a value at x equals a, then f is convex around x equals a. And if f double prime of a is negative, then f is concave around x equals a. Okay. So my favorite examples for convex and concave are f of x equals x squared and f of x equals negative x squared. So let's look at that. Okay. So if f of x is x squared, then the derivative there, f prime of x, is 2x. And the second derivative, f double prime of x, is equal to 2. Okay. So that means that for this function, the second derivative is 2 for all values of x. Okay. And since 2 is greater than 0, okay, that means that f is convex around x equals a for basically every possible value of a. Okay. So that means, we could say for the whole graph, perhaps, if we're viewing a graph. Okay, so here we have this graph, y equals x squared, or we could say f of x equals x squared. And we see that this graph, it's a familiar shape that we should know. We see that it's convex. That is, that the curve lies above the tangent at every point. Okay, so so here we have this. So I recommend remembering this example. Okay, because it's a function, it's easy to differentiate and see that the second derivative is 2, which is always positive, and also it's a graph shape that we're familiar with, and we see that the graph is always convex for all values of x here. Okay, so let's have a look at an example of concave. So we can get this just by multiplying by -1, so we get the negative of x squared, and then the first derivative is minus 2x, the second derivative is minus 2, which is always less than 0. Okay, so everything that we said where we use convex for the first example, it's true for the second example, except instead of it being convex, it is concave. Okay, so that is that this function is concave for all x, and if we show that, we see that. Okay, so the graph is concave. That is, the graph lies below a tangent drawn at any point. Okay, we could draw tangents at any point. The graph would lie below those tangents. So then we say that it's concave. Okay, right. So the next thing we're going to look at here is what about inflection points? Okay, so from our box on page 149, we have this information that if f has an inflection point at x equals a, then the f double prime of a equals 0. So the value of the second derivative at x equals a is 0. Okay. However, if you know the second derivative is 0 at x equals a, okay, then that does not tell us whether or not f has an inflection point at x equals a. Okay, so it may or may not have an inflection point there. Right. So that means that this situation with inflection points, we have to be a little bit more careful. Okay. So I've here are my two favorite examples. Okay, for so for both these examples, then the value of the second derivative at x equals 0 is 0. Okay. However, in this first example, there's an inflection point at x equals 0, whereas in the second example, it's a local minimum at x equals 0. So this illustrates the fact that that if the second derivative is 0 at a point, then there may be an inflection point, but they may not be. Okay, so let's have a look at these examples in more detail. So in this first one, we say, well, f of x is x cubed. So then the first derivative is 3x squared, and the second derivative is 6x. Okay. Now, if we think about 6 times x, then that is a negative value whenever x is negative. So that means the second derivative is negative whenever x is negative, which means that f is concave for x less than 0. And similarly, when x has a positive value, then 6x is also positive. So that means that this second derivative is positive whenever x is positive. So that means that that f is convex whenever x is positive, that is, whenever x is greater than 0. Okay. However, in this case, at 0, we have f double prime of 0, that is 6 times 0, which is 0. Okay. So then there may or may not be an inflection point. And if we look at the graph for this function, we do see that there is an inflection point at x equals 0. Okay. So an inflection point is a point where the curvature changes from being concave to convex, or vice versa. It could also change from being convex to concave. Okay. So here, we would also call this in Swedish terrasspunkt. Okay. And I've been using the word terrace point. Okay. So we say terrace point when the first derivative is also 0 there, where we have an inflection point and the slope is 0 at that point. That is, the value of the first derivative is 0. Okay. But if it's not a terrace point, it can still be an inflection point if the curvature changes from concave to convex at that point, or vice versa. Okay. So that was an example there where the second derivative was 0 at that point, and there was an inflection point at that point. Okay. In our final example, we say f of x is x to the 4. So the first derivative is 4x cubed. The second derivative is 12x squared. So 12x squared, that is positive. It's greater than 0 for all real x except x equals 0. So that means that f is convex for all x except for x equals 0. So we can say for x not equal to 0. That means for all x except for x equals 0. Okay. However, again, we have this situation that the second derivative is 0 when x is 0. But in this case, there's a local minimum when x equals 0. Okay. As we see from this graph here. Right? Okay, so I hope that these examples are helpful in helping you to use these theorems about convex, concave, and inflection points, and how the second derivative relates to that. Super, thanks for watching.